can you hear me? Yep. All right, lesbians in tech, hey. So, I'm Pri. I'm a data scientist at a public startup, which is within the government, the federal government, the Commerce Data Service. So I'm going to talk about failure in machine learning. I got a kind of conventional start in data science. I was doing genomics and stats. And data science is about intersectionality, right? It's about coding and statistics and domain knowledge. And being the queer, feminist woman of color that I am, as I was in the space, what I would notice is, like, I'd see the way we're using data science to address problems in the world. And every once in a while, kind of my queer spidey sense would tingle. And I'd realize that there's something about the application of data science to problems that doesn't always go well. So that's what I'm going to talk about. So when we hear about data science, usually from the media, it tends to be, privacy scares, which is fair. If you hear about it from quants or statisticians or data scientists, it's about how do you optimize statistically? How do you reduce your error rate? But I am going to talk more about that intersection, what happens when you try to apply data science. And also, we're going to start with what is statistical modeling, what is predictive learning. So we're going to do this for a second. So what we need to do, generally, is try to predict y with some set of predictors, x, right? So, and what we want to do is figure out what f is, because f gives us systematic information about x that you can use to figure out y. So if you wanted to know if someone was wearing a bow tie, you might use predictors like if they have a gingham shirt on, if they've ever used the word dapper, if they're at Lesbians Who Tech, and you'd be able to get some probability that they're wearing a bow tie. So that's an example of a statistical model, a predictive model. And we use them actually quite a bit. We use them whether or not to figure out if someone's wearing a bow tie. We can use them to see whether it's going to rain tomorrow, whether or not some email is spam or not, what you're likely to buy on Amazon, who you're likely to date, or if you're about to quit your job. Right? These are all examples of models, and they all have a big F behind them. But we also use statistical models to predict things that are a little more serious. Like we might use it to figure out if a returning citizen, someone that has been incarcerated, is likely to commit another crime. We might use it to figure out if you are likely to pay a loan back or if you are a good teacher. So I'm going to focus on the recidivism models because they're a pretty good example of a lot of what I want to highlight. So what these try to do is give some probability that someone is going to commit a crime again within a certain time frame. And they're implemented in loads of states in the United States. But the way they're implemented kind of changes. So sometimes they're used for allocating resources, preventative resources. So if you're given a high-risk score, you may be given a parole officer that has fewer cases so they can pay more attention to you. Or it could be used for sentencing or for parole hearings. So when you build a model, there are innate assumptions and limitations. And when you build it on the state level, when you have it affect large numbers of people, that scale up also means your assumptions and limitations scale up. So assumptions include things like the past looks like the future. Models generally take data from what has happened so far and try to extrapolate out what's going to happen in the future. So that means there's some ground truths that get set up when you build your model. Now, we have a prison system that is 58% African American and Hispanic, whereas those folks only make up 25% of the US population. So that ground truth is going to hold true in this model no matter what, and propagate it. The next is that more data is good. Now, you hear this so much all the time. And the deal is that statistically, there is a curse of dimensionality. The more variables you have, the less likely you are, or the less powerful your model becomes. But we have a lot of data on folks that have been incarcerated because they have fewer rights. So we collect more data about them. So when people build these models, they say things like, oh my gosh, my model is so great, look at how much data I have, which inherently isn't true, but it sounds really good. And then there is an acceptable error rate. So statistics is probability, right? When you have built a model like this, you pump out some probability that an individual is going to commit a crime. Now, what that means is that you inherently are giving people a probability, and a really standard, totally standard thing you do is you build your model, you take some data set that it's never seen before, where you know the outcome. You know if they committed a crime again or not. You pump it through your model, and you see how well you did. So this is kind of what that output might look like. And then folks that actually work in that field figure out, hey, these are my thresholds. This is what I'm going to call medium risk, low risk, high risk. But what you are inherently doing at that point is deciding that there is some number that it's OK to misclassify. And something I want to flag for you now is that something that has happened recently is judges will overturn plea deals between defendants and prosecutors because they saw the risk score, and they'd give them a harsher sentence. So we're coming up against some limitations of data science. It's great for mass parsing. It sucks for exceptions. So and on top of that, the kind of models we're building are black boxes, either because they're just hard to understand, but also, more often, because for-profit companies build these and then don't share their methodology because it's intellectual property to them. So if you are an exception, that means you have to go contest the score you were given, and the burden of proof falls on you and not on the model. And then we create, at the state level, at the national level, self-fulfilling feedback loops. Because you predicted that someone has a high-risk score, and they then did not get into some alternative treatment program. Instead, they were incarcerated again, which contributes to the likelihood that they commit another crime. And then they do, and then your model gets to pat itself on the back. Also, my goodness, so a lot of papers talk about how they found the race column from their data set and deleted it. That is not something you can do in this nation, right? There's no way to just exclude race as a factor. There are so many proxies for race, especially when you combine variables like socioeconomic, demographic, what zip code you live in, what crime you were convicted of. So it may not sound like it, but I actually really love data science. So one thing I want to flag is that we use models where we don't have enough resources. And when a system doesn't have enough resources, that also tends to be where we house our most vulnerable populations. So we have to be careful when we build these models because we're hurting our most vulnerable people. And we have to question the data gods. There is no inherent subjectivity in statistical learning because people build this stuff and our world is not subjective. Also, we need less homogeneous teams. We need teams to look more like the folks in this room, more like the actual world, because folks in this room are more likely to have a spidey sense and say, that looks more like systematic bias than some innocuous bureaucracy that you just made up. And we need transparency, like not open data necessarily, but open methodology. We need to know how people are building models and what assumptions they're making along the way. And we need to be skeptical. When people say that their model is super simple, it fits on a Post-it note, that they have so much data, and that it's scalable, that you can plug and play it anywhere, that's when we need to question the F out of that.